Good morning, good afternoon. Welcome everybody to August's Geomagic Tech Tips webinar. This is a monthly series where we get one of our experts on to take you through a workflow, a tool across any number of our Geomagic portfolio. Today, we're joined by Cullen Williams. He is one of our applications engineers based in the US out of Illinois. And today he's going to be taking us through a Geomagic for SolidWorks workflow, completing the complete reverse engineering of a cast pump housing. A couple of bits of housekeeping. If you've got any questions as we go through, feel free to add them in the questions area of the GoToWebinar control panel. We've got some time reserved at the end to answer questions that you might have. So drop those in there and we'll get to them right at the end. The presentation should be 35, 40 minutes, something like that. So there will be some time at the end for questions. So without further ado, I'll pass over to you, Cullen, and enjoy.
Perfect. Thanks, Guy. Yeah, so like Guy's saying, I'm an application engineer here at Octane. I have 5+ years of experience in the 3D scanning, 3D printing industry. We're going to be looking at this pump housing today, and we wanted to do something. I think a lot of people can get frustrated with these webinars. Sometimes there's a little bit too much man behind the curtain action going on. So we've got a full workflow here. And like Guy said, it's about 35 minutes worth of content, and then we'll have time for questions at the end. It did end up taking around like an hour and a half for the full workflow. So there is a lot of sped up video that you'll see, but it's all stuff that's like just mainly sketching and things that are more inherent to SolidWorks itself, as opposed to the Geomagic for SolidWorks plugin. So we're going to watch through this workflow that I've got here. I'm going to comment as we're going along. And like Guy said, if you have any questions or anything, please feel free and we can talk about those at the end. So here's our scan data of our pump housing. And I'm always trying to think, just like, how would I build this in SolidWorks if I wasn't even dealing with scan data? And so for me, that first feature is going to be kind of these two base flanges here, the 6-sided features here, and I'm going to be creating these reference planes. And so what I'm doing is I'm selecting these areas of mesh that you can see that are getting highlighted and using all of those points to average into a perfectly flat plane, because it's a cast part, right? There's not very much flatness really going on there. And a cool feature of Geomagic for SolidWorks, one, we're able to interact with the scan data, obviously, and two, on that particular feature, we have a snap to world feature. So all of those planes, as long as they're within like ±5 degrees of the world coordinate system, they'll snap perfectly to that. I believe that was like the XZ or the YZ plane. Now that we have those planes, we're going to start pulling mesh sketches, cross sections off of this data. So I can grab that plane 1, and I can make sure that that cross section intersects with the flange geometry that I'm looking to model, and it will create a polyline reference sketch that I can then use as a visual reference as I'm going through and building my sketch on top of this. So generally, I don't want to mess around with the actual mesh sketch itself too much. I'll leave that alone, but visually turned on in the background as I sketch my own new sketch on top of it. So here's where we'll start speeding things up, because most people know how to sketch and everything that's going on there. But as I have different tips and tricks, I'll definitely highlight those. So it is a little bit different of a sketching workflow, I'll say, versus like your traditional parametric part. And the reason for that is because we're trying to reference this scan data. So I'll pull some tricks with some things that might give you the heebie-jeebies, like throwing on fixed constraints and snapping directly to these kind of polyline splines here. But it's all part of the process to get this kind of organic data to rein into something a little bit more perfectly parametric, right? Another thing I want to mention here is that, as with any kind of 3D modeling project, there's 1,000 ways to get it modeled, right? You could model a cube 10 different ways. That gets multiplied even more for when you're talking about reverse engineering for scan data, because it really depends on what the goal of the application is, right? So what the goal that I'm simulating for this application is that we are trying to build a, what I call, geometrically perfect model, where things are flat, things are square, things are perpendicular, and all that sort of nice geometry, whereas like we can see from the scan data, nothing is really straight lines. It's all kind of wavy splines, but we're going to idealize it geometrically. but we are not going to idealize it nominally. So you'll see like that 9.93, I'm just gonna leave that. In practice, I probably would make that, depending on what I'm trying to do again, could make that a 10. But I unfortunately have a lot more experience in webinar design at this point in my career than pump housing design. So I'm gonna stay in my lane and leave the measurements as they are from the scan data. So if you know better and you're a pump design engineer and you know what you're doing, this is your time to shine and make that call that that's supposed to be 10 millimeters, right? So we have our first sketch for that flange made, and I'm going to use that last reference plane 1 to reference plane 4 to make too much body. And then we're going to come back with that center section sketch in a second and cut away that middle area there. So it's really a lot of this, like I said, we're trying to get almost in the head of the designer and figure out what the best feature setup to create this. And then we're using the scan data as a reference to get that built. So here, I'm going to do that same thing and get that mesh sketch going so I can get this slot sketched out and remove that material so it is looking more like the final product. You'll notice in that other sketch, I didn't center everything. That's another thing that I've learned that can sometimes come to bite you in the butt. If you do too much assumptions like that without knowing what you're doing, you can potentially cause some issues later on where things are supposed to be collinear and they're off by 0.1 millimeters, and then you get a weird surface and it takes a second to go dig and find it. It's not the end of the world by any means, but it's just lessons I've learned as going through and doing a ton of these things. There are certain features you can very easily just assume are flat or perfect or whatever, and then there's other features that kind of don't lend themselves to that unless you really know that that's what it's supposed to be, and you can justify why that's so different from the scan data. Right? So at the end of the day, the scan data is there as a guide. It's not running the show. You as the designer are running the show. So I use one of my, I like this function in SolidWorks where you do the opposite of the profile cut in order to get that center section cut out now. And we're looking pretty close for that middle feature, at least on the outer surfaces. We obviously have some work to do on the inner surfaces. But the main idea that I'm running with here is it should be about 3 main features, which is this center area, and then we're doing the second main feature is going to be a revolve, and we're going to follow it up with some lofting at the end here. So same process, grabbing that cross section. Here I'm just changing my mind because if you can see on that bottom left, the scan data was pretty incomplete for this little groove feature that I need to model here. So this happens a lot when you're scanning. Sometimes you don't get perfect data. Sometimes it's sent to you from somewhere else. And there are a bunch of tricks that you can kind of pull where you can reference different parts of the scan data and get it to work. But the best option is always going to be to rescan that area to make sure you're getting accurate data to the scan profile that you have. I don't have access to this part, unfortunately, so I'm making do with what I got. But if this was a mission critical project, I'd probably go back and make sure I had better scan data on some areas of this part here. Another thing in the sketching that I was talking about where we do it a little bit different, maybe from a traditional SolidWorks workflow, is you'll see that I do a lot of these I'm just kind of sketching in pieces. I'm trying to get each line segment where it's supposed to be, not really worried about connecting the endpoints to start with because it ends up causing more problems than you really want, and things end up snapping to things that you don't want, and it's just kind of a pain in the butt. So creating each individual segment and then coming back and doing some sort of a trim or a merge or something like that generally lends itself to a much more easy workflow, less of a pain in the butt, like I was saying. So you'll see that happen a lot here. What I was building there is we're actually going to do this as a single revolve. You could argue that it is 2 different features. We're going to do it as a single revolve here and kind of connect it in the middle with that little dummy piece of geometry that's at 10 millimeters that I had just thrown out in the middle. And that's going to go away when we do a boolean operation at the end with all these bodies. So you can see here I have all my kind of crazy sketch going on, and then I'm just coming through and doing power trimming and corner trimming in order to get my final geometry here. And same thing here, don't pay too much attention to what I'm doing with these dimensions here. I'm leaving them as is, right? And I'm also just kind of getting it to fully defined. So again, this would be something where somebody who knows a little bit more about pump housing design would know what would really be the way to call out these different kind of angles. Like I'm just kind of calling out what's there to get it to turn black, right? But I'm sure there are proper angular call outs on some of these grooves and things like that, or diameters. And that's really how you would build it. But the beauty of doing this reverse engineering parametrically is if you want to come back and change it at any point, it's super easy to do so. So finishing that sketch and revolving it, we've got our revolve feature, right? And we're starting to look a little bit closer to the final product every step of the way. Here, what I'm doing is I'm noticing that there is some geometry inside of that pipe diameter. You can see right there, kind of that sharp edge from the flange that's poking through. And that's obviously not geometry that we want to be there in the final product. So I'm going to do a little surfacing trick here where I'm going to grab the inner surface of that pipe, copy it, and I'm going to use that as a tool way down the line at the end of the workflow in order to trim that away once we do our final boolean. So I don't know exactly when at this point this is going to jump in, but I know this is a useful trick I use all the time, and I know it's going to come up at some point. So I'm doing that now. I know it's going to need to be done. No need to roll back and do it later. And I'm just going to save that tool in my back pocket when I need to further along the line. So you got those first two main features, and we're going to start looking at our third features, which is our lofts, or our loft and our loft profiles. Now for lofting, what I'm trying to do is I'm trying to put my cross sections at areas of changing curvature, areas transition points. So we're looking at modeling the inside of this kind of, call it horn geometry or funnel geometry on the end there. And we're going to work from the inside out. So what I'm trying to do right here is I'm dragging this cross section. I'm trying to get it to line up to that inner lastmost part of the loft, that sharp edge on the inside, in order to get as close to the scan data as possible. So I'm just, at this point, I'm just guessing and checking and seeing what kind of a offset would be correct from the front plane there. We're at 73, we're getting closer, dragging it around, not quite there. And we'll land on 80 here. And that looks like it's about right. I mean, again, it could be dependent on if you are modeling it perfectly or you're really trying to get, obviously millimeters versus inches would make a difference here as well. But like I said, the saving grace is at the end, we're going to do an accuracy check, and we're going to be able to check ourselves and all of our assumptions and make sure that we are within the tolerances that we expected for this kind of a part. And with this being a cast part, generally we're not looking at super tight tolerances here. So that's why most of this, like assume things are centered and assume things are flat, this kind of idealization generally works very, very well for these parts because they are so rough to begin with. So you kind of have to do those assumptions in order to get something that's a reasonable kind of model. So my second profile here, normally if you have a loft, you have a minimum of two profiles, right? The start and the end. And just looking at the geometry, I can see that there is a very distinct change in curvature right about here. I think I end up, is this 48, I think? Yeah. Right about there, 48 millimeter offset is another distinct change in curvature. So I want to make sure I have a profile there to define that as well. And then the final one is just going to be a super slight offset from the front plane to get that circular profile. And from here, it's the same kind of mesh sketching process that we saw before. The first profile is going to be this kind of rectangle with filleted corners. Here's what I'm talking about with different kinds of idealization. So I'm grabbing this edge that I know is supposed to be collinear, where I think the scan data like very specifically didn't line up with this line in this particular area because there was like weld or something like that that was adding extra material that really shouldn't be there where we put the cross section, even though we know the design intent was really for those two surfaces to be coplanar. So I'm grabbing that from the solid body as opposed to the scan data body. Same thing for the second profile here, very similar, different sized rectangle with different size fillets, but same basic profile. And then I'm going to do something a little funky. You may or may not be familiar with this kind of golden rule of thumb with lofting, but you might think that, oh, you just need a circle and you're good to go. You really want to have your loft profiles to have all the same number, at least the same number, if not the very similar structure in terms of sketch entities. So each of these rectangles with fillets had 4 lines and 4 arcs to make up their profile. So I want to have 4 plus 4, 8 entities. Like I said, ideally they'd be lines and arcs, but obviously that's not the same profile at all, and it would give us bad data. So we're doing it all with arcs, but I'm trying to just generally line them up. That's what that first 30 degrees and 60 millimeters was. I'm just trying to line up that corner area so that the points kind of flow along the loft properly. So I split that single circle into 8 arcs actually, so that it behaves a little bit nicer with the loft. And leaving it as a circle, it would probably work fine, but I've definitely had times where lofting can be complex enough as it is, and just giving the system exactly what it's expecting as served up on a silver platter as possible generally just leads for less headaches down the line. So we've got our 3 profiles. We're just going to throw a normal to profile constraint on the start of the loft there, just to get what we're looking for out of that type of feature for the inside of that funnel shape. That's looking pretty good. Save early, save often, always. Now I'm going to do, I'm going to use the inside surface to create the outside surface. And the reason I'm doing that is if you look at the scan data, and we'll see further on, it's not really a perfect offset from the inside surface. And this is where I am doing this idealization. So my thought process is that, yes, if we wanted to be green accurate to the outside surface, we definitely could do that with another loft. It's double the work, right? It's 3 more sketch profiles minimum and a whole nother loft feature on something that maybe it's an as cast surface, right? So maybe if it's not exactly like the inside surface, it's just kind of has to have a thickness and it's there. The inside surface being much more critical to the application. The outside surface is just providing a thickness to the body to withstand the forces of the application. And here, right there, if you saw that offset, that should have been my first clue. I didn't notice it, I guess, the first time I was going through this, and we'll see how I deal with it. But that's a hint to some issues we'll have coming up with that loft, where things that should be smooth and nice aren't, and there's a reason for that in the loft building process. But that's what this is. This is like I said, there's no man behind the curtain. I'm trying to just show you guys, this is the full process of someone sends me some scan data. Can we get a reverse engineering model done? And what does this look like as I'm going through this process? So what I'm doing now, I have the inside and the outside loft built, but I'm not going to use those until I have the entire body booleaned together. And then I'm going to cut those out and add them in. So what I'm working on now is checking this offset for the outer surface, which was, if you saw there, it was just a rough measurement of like 6.75, I think it was. So I'm going to call that 7. So that's going to be my offset, as I've created a copy of that inside loft. And always good to use naming conventions to make sure you keep things straight. So I call them inside loft, outside loft, make sure I'm not offsetting the wrong one. And here's where that issue I was hinting at is rearing its head. So 2 millimeters offset, fine. I go to do 7 and it's squawking at me. And looking at this, I'm like, this is not really any sort of fancy, funky surface. I wouldn't expect there to be any error. So let me go check what's going on in the loft. And this is exactly what's going on. So even though I ate my vegetables and I did the proper thing and I broke that circle up into 8 spaces, it still gave a little bit of twist in the intermediate points, because when you build the loft, you just have that one control kind of polyline, and the rest of them got swirled for whatever reason. So going in there and just fixing that up so that it is properly continuous instead of twisted allows us to do this offset properly. So there's our outside loft finished. And we should be good to boolean. I think I might tweak it just to move one face a little bit further, but at this point we're almost ready to boolean. Oh, you've got to trim that outer lip on the front plane as well. That's poking out too far. So turning on that solid body just to make sure I have a reference. So there I'm checking. It's just a little close for comfort. I just want to make sure that that's way far past there for the combine to make sure there's not any sort of super sliver of edge that didn't get combined properly. I'm just going to push that in a little bit further. And then here we're going to trim that lip of the outside loft geometry just back, make sure it goes, that it's buried within the revolved geometry. And I always laugh because I use this surface cut all the time. It's one of my favorite tools. And I think I have like far less than a 50-50 success rate with guessing which way it's going to go. I should memorize it by now, but I use too many different softwares and it's too easy to go back and edit it. But yeah, I pretty much always get that wrong on the first try to the point where I don't bother guessing anymore. But after a second try, we get it correct. And now it's well trimmed and we can go through our boolean. We have our 3 main bodies. We're not dealing with that inside loft yet. So we got our boolean and we're going to start cutting things out. We're going to deal with the center flange area first, I believe, and then do that pipe on the left and then the loft as a final thing. So here I'm just looking for, if I can use an old mesh sketch or an old reference sketch, I always try to. It can get a little cluttered if you just kind of get a little crazy with just adding mesh sketches. So it's just a little easier to see what's going on and make sure you are dealing with what you want to deal with, right? And not mistakenly using the wrong sketch can be a pain in the butt sometimes. So it's kind of similar to the loft where I'm doing an offset of that profile just to make sure it's perfect and it has the correct wall thickness there. And then this is another idealization. I believe this is actually a little too shallow. I think it needs to be like, I think it's like a 1/4 millimeter or 1/2 millimeter deeper, but I'm calling it equal to that outer flange face because that's close enough. And that's really what the design intent most likely was. We're trying to have that piece be a single thickness, right? So now that we have this center area chunked out, we've got two sets of features in here. We have these holes and we have these little slot indentations here. So to do the holes, what I'm going to do is just kind of use this, instead of doing a mesh sketch here, I'm going to do this kind of visual overlay, almost like a silhouette here to try and do this. And I'm going to preface this by saying, if you actually look at the scan data here, you can see very large chunks of the sidewalls of these holes missing. And for a hole, the sidewall is the most critical scan data by far. So this is something that I'm putting in there just to show how I would do it. If this was for any kind of application that mattered, that I wouldn't even include this feature. It needs to be, unless it was like something standard, it needs to have that scan data there. So this would be a rescan on these features here, just because we know information about what's going on. I've got an idea that there's 2 holes and they're kind of this size, but it's just too much unknown without having a lot of the sidewall information in there. So this is more of a exhibition feature, if you will. So same thing as before, I'm just going to use this, kind of visually line this up, show my scan data again, hide my solid bodies to see what's going on. And you can see it's really not just as simple of a hole as I'm calling it here. You can see there's some like groove features in the top surface there, and it's a as I'm putting this chamfer on, it's a hole with a chamfer in it. So we're missing a lot of information on this feature. That's something I always do if I'm guessing and checking numbers. I always kind of jump around and hone in on that 13, then check 12, then check 11 first, and then just make sure everything is, you're not assuming going one way or the other. So we've got those holes in there. Now we're going to look at doing those 2 slot features. Very similar to what we've been doing so far, nothing super fancy here. Right here, I'm just checking to see what, out of curiosity, what that flange thickness is, and it's 13.23 off of that 13 that I entered. So I'm calling that close enough that that's a quarter millimeter off. We could go back and call it 13.23 if we wanted to, or we could make that flange 13 exactly, right? But we just grabbed those planes directly from the scan data. So now our trick for this is you got to be very careful about where we do our offset. So if we go too deep, we're going to miss those slots. If we go too shallow, we're not going to get enough of a proper outline there. So this is really touchy. We're trying to, especially with this being all not only rounded out from, I'm sure it's a filleted feature on the actual physical model, but when you scan things, they get a little bit rounded out as well. So this is a very touchy cross section. Just have to offset it just right to make sure you get the correct profile there. So same thing, I'm idealizing that to vertical on the origin and then make these guys equal and symmetric. But numerically or dimensionally, we're leaving them as is. And then here I'll do a similar kind of guess and check on the depth there. Again, we'll go back with the color map and make sure it looks good in the end. But here it's, you can get pretty good at checking it visually with the scan data here, where what we're going to try to see is just like we'll see on top surfaces here, we want to see a mixing of solid body and scan data. And that's going to tell us that that surface is basically intersecting with the scan data at that point. So I'll turn on the scan data here in a second, and we're going to see how good we're intersecting with it. So you can see those top surfaces on the flange are like kind of orange peeled between the 2 surfaces, but the slots that we're dealing with in the middle are not. So that's going to tell me that I think it was 1 millimeter is not deep enough, and we're looking for that to go a little bit more. So now you can see I get, maybe it's a tiny bit too deep, but I'm getting some intermingling there. And then we're going to add some filleting on here too. That's going to bring it much closer to that final scan data. All right, there we go. Now we're using that surface offset that I hinted at earlier, because you can see we still have that combined geometry that we don't want in there, just a little bit of edge corner there. And what that's going to do is trim that out for us. So we can cut with surface off of that surface offset. I think I get this one correct. So I'll give myself a pat on the back here. And I even did change it, so I knew what I was doing apparently. But nice. Now that inner diameter is nice and cleaned out, and that's looking good. We can hide or eventually get rid of that. And now we have this inside loft to chunk out. And there we go. Lines up nice on that bottom edge. Looks like a nice smooth surface. So at this point, the model is looking beautiful, and we want to make sure that it's not only beautiful, but accurate. So we're going to do an accuracy check here in a second. Now, what I always like to say about these accuracy checks is, so green is obviously good within our tolerance range. Red means we're too much material. Blue means we're too little material. But these are much less of a report card, if you will, and much more of a heads up of what's going on, right? Because there's plenty of times where I deviate from the scan data and I get all sorts of red and blue all over the model, but it's for reasons that make sense to my application. So I'll have a deviation here that I'll call it justify away because it's what I'm looking for. And you can see I'm pointing out, obviously we're missing some filleting in there. We got all that blue, but we're seeing some red high spots and blue low spots on the outer surface of that loft. So what I'm thinking right now, and then we see these two large red spots on the inside of the loft. So these are totally need to be fixed. That's another loft profile that needs to be added. But those blue and red spots on the outside of the loft feature, those are what I'm going to focus on, is just making sure that the wall thickness is big enough, right? Because remember, we are going away from the original design. I mean, this kind of looks like it was maybe hand built, and going with that offset instead of doing a second loft. So I expected there to be some deviation. What I just didn't want to do is I want to make sure that we didn't take away material in areas where it could be critical. So I'm going to bump that offset from just up a millimeter just to see how close we're getting then. And that should give us a little bit more wall thickness to make sure that at least we're getting rid of the blue spots on that surface. Now for this inside surface, generally with a loft, like I said, I'm placing cross sections at areas of changing curvature. And usually that's good enough to get what you need. But obviously here we missed some behavior in the middle there. We could do another guide curve, or we could do a guide curve, or we could do another cross section. I chose to do another cross section. And the way that I placed this is really you want to put it, there's two ways I'll do it. I'll either do like halfway in between a cross section, just as like a nice clean mid-plane thing, or I'll just try to center it directly on where the deviation is the largest. And it turns out that centering this on my call it like the last profile, the circular one that was the 1 millimeter offset, and then the 48 millimeter offset, so call it 25, that ended up being like right where it needed to be intersecting those two large red spots there. So I got to do both of my different options at the same time there. So same process as before. We're just creating that mesh sketch in, from the offset, and then we're going to do our own sketch on top of it. And this is a good sign that we're on the right track, that this profile is so different from the other two. So we're going to see it's not the circle and it's not the rectangle. I'm actually going to use only arcs to do this. I think the technical term for this is closer to squircle. But we're going to use all arcs here. And that's the reason I like that is because it shows that it is a totally different profile. This was a profile that was missed while we were building it the first time, that has very unique geometry to it and wasn't being represented before. So by getting this new curvature in there, hopefully we should be able to get a lot closer to that final, or get rid of those large red marks, right? And get closer to that final geometry. Because that inside surface is much more critical, in my unprofessional opinion, for the pump housing, where flow and things like that are going to be affected. Whereas the outside surface, as far as I understand it, is just for structural integrity. So going a little too heavy on the outside surface isn't going to hurt anything. Having bad geometry on the inside could potentially affect performance of the part. So now we've got our 4 profiles. Just going to rebuild the loft that same way and cross our fingers. Looking good. Now I'm just being extra paranoid, checking for any of that twist again. Doesn't look like there is any. I'm going to let these go through, rebuild, because I expect an error there. If there was any twist, they rebuild fine, so that's a good sign. Now I'm just going to rip it to the end, and everything should be good. Now we'll go back to our color map just to double check what we did for those 2 edits. And so we can see on that outside loft, all of that blue has gone away and is replaced with just a little bit of red, nothing too crazy. And that's what I was looking for, right? We just want to make sure we weren't too thin. If we're a little heavy, is what it is. We have to be one way or the other. This is the price we pay for getting a cleaner model with an offset surface, as opposed to a second loft, which would be, if you're trying to do any kind of edits or anything, that second loft is going to be such a pain in the butt unless you do a lot of work to link it parametrically to the first, which is almost the same thing as doing the offset, just more steps. And the inside, we were able to get rid of those red spots much nicer. So here's the final model after we just throw on our cosmetic fillets here. Like I said, whole process ended up taking like around an hour and a half with backtracking and screwing things up and kind of more like a realistic timeline, right? And then we pulled it down to about 30 minutes, speeding up through things. So obviously that sketching can take quite a while if you got a lot of details to go through. But at this point, we're done with the workflow. Hopefully that was interesting to everybody, and we'll open it up to any questions. So do we have any come in, Guy?
Thank you, Cullen. We have a couple here. So the first one, obviously that part is a single part, but can you reverse engineer assemblies as well?
Good question. So with assemblies, Geomagic for SolidWorks plugin doesn't work with assembly files. But if you are able to do call it like a pseudo assembly by modeling a multi-body part, which I end up liking a lot more of the time, to be honest, you can have multiple different scan files and assemble them together in Geomagic for SolidWorks. It's just all within a part file. So you can't have an assembly file, but you can have a functionally similar assembly all within a .prt file.
Great. I guess this one kind of follows on from that. Do the scans that you bring into SolidWorks need to be aligned, or can you align them when they're in Geomagic for SolidWorks?
So somebody caught me. Yes, I did use pre-aligned scan data for this one just to save on time. But no, Geomagic for SolidWorks has many different alignment tools that we could go through. Like I said, I was trying to keep time reasonable today, so we skipped that part of the process. But yes, Geomagic for SolidWorks can totally do alignment for you. Or if you bring it in pre-aligned, that works too, just like I did.
Great. And the final question we've got here is around SolidWorks support. So I'm not sure which version you were running in that example, but
up to date always.
Yeah.
I was running 2023. And the question is, how far does support go?
Yeah.
I believe that's back to 2019. So SolidWorks 2019. I've heard of other people running it on earlier versions and it not having too many issues, or it's been okay, but the officially supported is back to 2019. But we can get you trials and can try it out if you have earlier versions for whatever reason.
Perfect. I think you must have done a good job of answering any questions. That seems to be the only ones we've got. Thank you everyone for joining. Appreciate you taking the time. If you think this is going to be useful for anyone else that wasn't there today, then you should receive the recording tomorrow. Feel free to pass that on to anyone you think of interest, and look out for the invite for September's Tech Tips webinar, which will be probably 2 weeks time. The invite will go out. Look out for that, and we'll hopefully see you then. Thanks, Cullen, and thanks everyone.